morning everyone. In last class we finished about the different types of couplings. So what is meant by electrical coupling, what is meant by magnetic coupling, and how we are going to connect, and how we are going to implement the dot convention, and what is meant by quotient of coupling we seen in the last class. So once again I'll repeat the quotient of coupling, and next we'll go for how we are going to derive the how we are going to connect a transformer, what is ideal transformer, and how the T networks for the magnetic networks or magnetically coupled circuit, how we are going to implement the T networks. So this is your today's class. So by this your first chapter will finished. Okay, so quotient of coupling. Some magnetic flux will be generated due to the voltage induced in that particular coil. That magnetic flux will be induced in the second coil. So that induction of the magnetic flux in the another coil, that is called as coupling. That there we are going to define one quotient, that is called as a quotient of coupling. So we derived that quotient of coupling. So that K, we are going to indicate that quotient of coupling with K. So K equals to M by under root of L1 L2, where M is the mutual inductance of that particular magnetically coupled circuit, L1 is the self-inductance of the first circuit, and L2 is the second self-inductance of the second circuit. So this is about your entire quotient of coupling or mutual inductance or self-inductance, whatever it may be. Here, by using the self-inductance and mutual inductance property, we are going to design one basic electronic device that is called as a transformer. Transformer, you already know, you already came across with the construction of a transformer. A transformer which consists of two coils. One coil is called as a primary coil, second one is called as a secondary coil. Okay, so primary coil is connected to the input, so from the secondary coil we are going to get the output. So if let us take the number of turns in the first primary coil, that is N1, the number of turns in the secondary coil is N2, let us take. If N1 is greater than N2, then that is called as a N1 is greater than N2, nothing but in the secondary coil we have some less turns. So that voltage, whatever we connected to the input, that voltage will be stepped down, that voltage will be decreased. So decreased means that called as a step down transformer. Okay, so if we have some secondary coil number of turns will be more when compared to the primary coil, then that is called as a step up transformer. So how we are going to relate self-inductance with the that number of turns, that ratio we are going to calculate in the ideal transformer. So basically you remember this thing, the transformer having the two turns, one is the primary coil and the secondary coil. If secondary coil is having the less turns, then that is called as a step down transformer. If that secondary coil is having the more turns, then that is called as a step up transformer. Okay, so now I am sharing the whiteboard. So in this we are going to learn about the ratio, how we are going to relate the ratio between the self-inductance and number of turns. Okay, so let us see that one. So here first ideal transformer. So I already told ideal transformer which consists of two coils. So let us take this is a first coil and this is a second coil. So here you apply voltage as V1 and here you apply voltage as V2, let us take. So here the current direction I2 and current direction I1, so the both are entering at the dotted terminals. Let us take the mutual inductance value is M, and here that inductance value let us take L1, and here inductance value is L2, let us take. The quotient of coupling value let us take, that is K equals to 1. So we can represent this with a coil construction also. So let us take, this is a magnetic core. So for this core I am going to wound the coil like this. Okay, and here also I am wound. winding the coil number 2. So from here I am going to apply current I2, and from here I am going to apply current I1. So the voltage here, that is represent V1, and here voltage V2 let us take. Okay, so same, so we can represent dot also here. So here that current entering at the dotted terminal, and here also current entering at the dotted terminal. Okay, so here, so write the self-inductance values, or we can write that V value is equals to that V voltage. What is the voltage in the inductor formula? V is equals to L into di by dt we can write. So by this inductor L, that is equals to 1 by V into di by dt, whatever it is. So here we can express the voltage by number of turns also, n into d pi by dt. Okay, so this is a voltage formula, and this is also voltage formula. So we can equate these two. Yes, we can equate. So when you equate this one, what you get? That L into di by dt is equals to n into d pi by dt, where dt will cancel out. So what you get here, that inductor L is equals to n into d pi by di. Okay, inductor L is equals to n into d pi by di. So here, but what is a flux? Flux, that is flux pi. We can take it as number of turns into current by reluctance. Okay, by reluctance. So if we substitute this value in the above equation, L equals to n into d by di, that is du of di into pi value is ni by reluctance. Okay, we can take like this. Yes. So or else here I will cancel out, nothing but if this value is, let us take it as I, then this value, this total value, if we take it as I will cancel out here. So what you get here, L is equals to n square by reluctance, n square by reluctance. So here you can observe what is the relation, L is equals to n square. So if reluctance is constant, no, so reluctance is constant, so if we remove that constant, L is proportional to n square, nothing but L1 by L2 is equals to n1 square by n2 square. We can write like this. So this n1 by n2, that let us take it as A, where A is called as a turns ratio. So A is called as a turns ratio. Okay, so or else we can represent this one in terms of voltage also. So we can relate this. This is a self-inductance value. If we relate this one with the voltage. So in order to relate with the voltage, so we can take some pi 1. So pi 1 value as n1 into pi. So pi 2 value, that is in the second magnetic flux in the secondary coil. So we can take n2 into pi. Okay, so here, but we have that v1 is equals to d pi 1 by dt, or else v2 is equals to d pi 2 by dt. Okay, so if we, by taking these two, what we get, that v1 by v2 equals to n2 into d pi by dt by n1 into d pi by dt. So here v1 in terms of d pi 1 by dt, and here we get n1 here, and here also we can get n2 here. So if we write this one, write v2 by v1. Okay, so v2 by v1, nothing but what you get, n2 into d pi 2 by dt. So v2 by v1 I am writing, so n2 into d pi 2 by dt by n1 into d pi 1 by dt. Okay, so here if we simplify that one, then this total will be cancelled out, that v2 by v1 is equals to n2 by n1, n2 by n1. So n2 by n1, that we already know that value is a square, that n2 by n1, n2 square by n1 square, value is a square, that is turns ratio. So here n2 by n1 is nothing but that value is a. Okay, so if we take the circuit, here I am going to calculate the impedance of that particular input impedance of a transformer by taking one same circuit which is having one primary coil and another one is a secondary coil. Here instead of getting, here I am going to connect a load resistor, so that is ZL. Let us take the direction of current I2 is like this, just I am taking opposite in the previous case. So current I, so here input V1 let us take, and here that is L1 and here that dot, so this is a V. So from here I am going to get V2 voltage, let us take. Okay, so if you write the voltage equation in the first coil, so in the first coil what happens in this one, that voltage, this is a loop, voltage, input voltage, whatever the self voltage, that is self induced voltage in the inductor L1, and what is a mutual voltage in by the inductor L2. Okay, so that we are going to write. So first here V1 equals to what is the voltage in the inductor L1, that we are going to write j omega I1 into L1. So here that mutual inductance, these two directions are opposite, right? One current is entering at the dotted terminal and second current is leaving at the dotted terminal. So mutual inductance value is minus. So let us take the mutual inductance value is M here. So what happened, that j omega M into L2, j omega M into L2. So here in the second coil, this in the equation in, or this is in coil 1. So let us take, let us write in the coil 2. Coil 2, that is, here there is no voltage, so all together equals to 0. So first, what is the self inductance in the L2, that j omega I2 into L, j omega I2 into L. Next one here in the current, that is JL, the voltage in the load resistor, that is JL. So JL into I2. What about the mutual inductance? Those are opposite, right? So J omega M into L1. J omega M into L1 equals to 0. Why? Because there is no voltage, right? So here, if we simplify this one, this equation, the above equation, so take common here, J omega L, J, so here this is L2, right? This is L2 and this is L1. So from here j omega I2, so j omega L2 into I2, so j omega M into L1, so j omega I2 into L2, and here, so these two terms I2 will take it as common, so j omega L2 plus ZL equals to j omega M into L1. So we can write the equation I2. So j omega M into L1 by j omega L2 plus ZL. So say this is equation 2. So what is equation 1? That you have j omega I1 into L1 minus j omega M into I2. So j omega M into I2. So here you substitute this equation, equation 2 in equation 1. Substitute equation 2 in equation 1. Then what you have, that V1 is equals to j omega I1 into L1 minus j omega M into I2 value, that is j omega M into L1 by j omega L2 plus ZL. Okay, so if you simplify this one, already you know that input impedance is equals to input voltage, that is V1, input current that is I1. So we should calculate this one, V1 by I1. If we calculate for V1 by I1, then you will get the input impedance. Okay, so that is Z in equals to j omega L1 plus omega square m square by ZL plus j omega L2. So same thing, that is denominator. Here j, that j square, so j square value is -1, so this will become plus. So omega into omega, that value is omega square m square, and here take I as a common, so take I1 as a common. So what I1 value here, this is I1 and this is also I1, so take common and that will send to the another side. V1 by I1, that is equals to Z in you get, and here j omega L1 plus this term. Okay, so you already know that quotient of coupling. Quotient of coupling, what is the value of quotient of coupling? Which is k equals to m by under root of L1 L2. Okay, so by this one m, what is m? So m is equals to, or m square is equals to k square into L1 L2. You can write like this. So substitute those values here, then you will get Z in value is equals to j omega L1 plus omega square L1 square a square by ZL plus j omega L2. Okay, so here by this one, what you can observe here, directly Z in we can get as j omega L1 Z1 by j omega L2 plus ZL. Okay, so here Z in, so Z in value, if we neglect this one, then j omega L1 into Z1 by j omega a square L1. So here a square total will cancel out, so Z1 by a square you can get. So Z1, that a square is nothing but N2 by N1. So we can write that N1 by N2 whole square, N1 by N2 whole square into Z1. So we can write Zn is equals to N1 by N2 whole square into Z1. Okay, are you getting? So by the relation, what you have? So here Z1 is nothing but ZL, load resistance, ZL. So by this one, you can take that input impedance, which is proportional to the ratio of input impedance. Input impedance is proportional to the ratio of turn. So turns ratio. This is very important. So here we relate the relation, that is first one relation is L1 by L2 is equals to N1 square by N2 square, or else V1 by V2 is equals to N1 by N2, or else this is also called as turn ratio, that is A square A. Next Zn equals to N1 by N2 whole square into ZL. So we written these three relations. So next one, which is a T equivalent circuit. Excuse me. So equivalent T network for magnetically coupled circuit. This is the last topic in this chapter. So let us take the T network. This is a T network. Wherever two coils are there, we can draw like this. So here, this is the T network, and these are the impedances we have. So wherever two port networks are there, then you will get this one. So here V1, let us apply here, let us apply that V2, and here let us take this is Z1, Z2, and here Z12 or Z21 you can take. So here current direction is I1, and here in this one current is I2. Okay, so this we can implement, or this we can write it as like this also, which is having a two ports. So one block we are going to represent here, one side, or represent the input ports. These are called as a input ports, 1 bar, and from here I am going to represent the output ports, 2 bar. So here I am going to indicate the current I1, and here that voltage is V1, let us take. From here current is I2 and here the voltage is V2, let us take. So this is a two-port network. So if we write the two-port network equations for the impedance parameter, then what you can take, impedance is nothing but Z equals to V by I. So like same thing, input impedance, that we can write it as input voltage to the input current. V1 is a input voltage, I1 is a input current. So in the same way, Z output, that output voltage to the output current. So Z output equals to V2 by I2. Okay, so impedance, these parameters are called as a impedance parameter. So this is a magnetically, we can write the circuits or equivalent T networks for the magnetically coupled circuit. You can get these in detail in the two-port network chapter, that is in third chapter. Okay, so there we'll discuss in detail. So this is about your first chapter. You learn everything in the first part of your first chapter, that you are having entirely graph, what is mean by graph, what is mean by network, and how to write the incidence matrix, and what is mean by cut set matrix, and what is mean by tie set matrix or RLC basics. So these are the first part of your first chapter, and here totally magnetically coupled circuits you learn. So magnetically coupled, electrically coupled, and what is mean by T equivalent circuits, and next what is ideal transformer, and what is a self inductance, and what is a mutual inductance. So you learn all these topics in the first chapter. So in the next class we'll go for the second chapter. Okay, thank you.